All right, there we go. So today we are doing our Wi-Fi 101 webinar. This is sort of a how Wi-Fi works webinar. So it's kind of dry, it's kind of boring, but it helps explain a lot of things that are going on in Wi-Fi that maybe you don't know, or maybe you just need a little bit of a refresher on. We will be talking a little bit here towards the end about Wi-Fi 6E and Wi-Fi 7, but for the most part, what we're doing is we're talking about Wi-Fi in general, not any particular technology, not any particular products. So if you have any questions as we go through today in the Zoom interface, use the question and answer box to send in any questions you have. Depending on how things are going, I may or may not answer them as we go, or I may hold off and answer them at the end of today's webinar. There's a lot of slides, so I'm going to go through it fairly quick. So feel free to type in any questions to slow me down or let me know where maybe I wasn't being as clear as I could have been. So we'll start off just for any of you that might be joining us today that are not familiar with Zyxel, new partners, etc., those watching on Facebook. So just a very quick background. Zyxel has been making networking equipment for over 30 years. We got our start all the way back in 1989. Um, our biggest business has been selling CPE devices, those routers and other devices that would be provided to you by your ISP. But we've also been doing what I'm going to call SMB networking for the last 25 years, maybe, certainly 20 years. And when it comes to Wi-Fi, we've been making Wi-Fi products since the very beginning, since the late 90s. Back before there was 802.11a and B, there was just 802.11. We were making those products. We also used to have our own chipset manufacturing, or R&D, I guess you'd call it, as well as manufacturing. That got bought out and sold to Atheros. Atheros then got bought out or sold to Qualcomm. And so some of those patents are still being used today in anybody's products that you buy that use Wi-Fi. So we'll start off here with the very basics of Wi-Fi. And we'll start by hitting off here with the timeline here. So this is the Wi-Fi timeline. As you can see, 802.11 got its start all the way back in 1997. And that's partially why we have a number of the Wi-Fi issues that you've probably run into over the years when doing Wi-Fi. So basically, when 1997, when they were creating Wi-Fi, we didn't really have video streaming, audio streaming, voice over Wi-Fi. It was just low-speed data connections between devices on your local network for sending emails, transferring small files over FTP, things like that. And so since that was what went into what they expected the network utilization to be, that's how it was designed. It was designed basically to be lightweight, to minimize things in order for it to work. And unfortunately, because of that, there's a lot of legacy issues with Wi-Fi that can trace their roots all the way back to that original first draft or first spec back in 1997. It was only with Wi-Fi 6 802.11ax in 2019 that we started to see some of the major issues with Wi-Fi being addressed with the new updated Wi-Fi specs. Everything else between then A, B, G, and AC has done very little to solve some of these core problems with Wi-Fi. So that's now starting to be addressed here. So when we're talking about Wi-Fi, there's a couple different names that you will see pop up from time to time. The first one is IEEE. They are the guys who create the standard. So this is a group of engineers, industry involvement, and they create all the standards for how things work when it comes to networking, and that includes Wi-Fi itself. So that's where the 802.11, some random letters, comes from. That's their naming for their standard and how it's referenced in their documentation. So that's IEEE. They create the standards. There's the Wi-Fi Alliance, which is more of a marketing group that came together in the early days of Wi-Fi to deal with the problem, which is no matter how much time and effort the IEEE spends in trying to define how things work, human language is imprecise. So people may interpret certain requirements differently in how to implement them, or you may just get vendors who decide to skip parts of the standard causing incompatibility issues between different vendors. So the Wi-Fi Alliance was formed to basically create a group that would also, on one hand, help market Wi-Fi to the general populace, but also to create some standards and interoperability testing on top of IEEE to verify everybody's products can talk to each other. So they're the ones who give you that Wi-Fi certified logo that you can find on a lot of consumer products. You generally don't see it on business class products. So they create certain tests that you have to go through to get certified, and they maintain a list on their website. And what's required to be Wi-Fi certified changes from time to time, but the general idea is to make it, so you don't have to worry that I've got an Intel chip in my laptop, I've got a Qualcomm chip in my phone, and I need them to be able to talk to each other and talk to the access point, who's maybe a Qualcomm-based chipset. So this is a way to make sure everybody talks together and sort of enforces the IEEE and fills in some of the gaps there. And then there's the FCC. So the FCC is there to set rules for anybody who wants to broadcast radio frequencies, whether it's a TV station, radio station, or you yourself doing Wi-Fi. So they'll tell you which frequencies can be used, what powers can be used, and how to implement those sort of things. Cover things like frequency bleed over, stuff like that. Now, in general, the FCC requires manufacturers like us to self-certify. So we have to go to a third party, submit our product, get a certification before we can import and sell the product here in North America. Now, the FCC very rarely does their own independent testing or validation. There was a case a few years back where a certain vendor, who will not be named, was selling products that were way out of the Wi-Fi spec, much too much power for what is allowed under the rules. And that was why they were dominating a lot of Wi-Fi performance tests. And they ended up having to be sued by one of their competitors to force them to follow the FCC rules. So, the FCC sets the rules and they sort of hope that everybody follows them. These set rules for if you want to add antennas to an outdoor access point, for instance, how to calculate, the max gain and things like that. But you're very rarely going to find someone from the FCC coming to your installation and checking to verify you're broadcasting correctly. But if you do get caught by the FCC, it is big time fines. So now we'll talk about radio waves. So we use radio waves for Wi-Fi. And just as a general rule, as frequency goes up, the easier it is to encode more data onto it. This is something that's kind of gone away with modern technology, but historically that's been the case. That is why 802.11a was faster than 802.11b, for instance, when they both came out at the same time, in part because of that. But also, as frequency goes up, the lower the range. So I'm old and ancient, so I remember the days when cordless phones were sort of cool and new and exciting. So back in those days, cordless phones operated on 900 megahertz. Sound quality wasn't too great. You may occasionally get to hear one of your neighbor's phone calls, especially if you're in an apartment. But the range was fantastic. You could get on the phone, walk out into your yard, maybe walk across the street to your friend's house and be able to maintain a phone call. Over time, we saw a move to 2.4. I think this is in the late 80s, early 90s. And 2.4 gigahertz is higher frequency than 900. So what we saw is an improvement in the sound quality, but we saw the range drop. So maybe now you couldn't go across the street, but you could probably still be able to talk out in the backyard without any issues. And then in the early 90s to mid 90s, there was a big push to move to 5 gigahertz. So again, call quality got better, but range got less. And those of you with big giant houses maybe found that your phone could not be used in every single room in your house because the quality was signal strength wasn't there. And that's why it has a lot to do with the frequencies being used. Now there's some other factors that fit in there, such as available bandwidth, things like that. But in general, that's just a good rule of thumb to help understand it, especially if you're old like me and lived through these changes. So when it comes to broadcasting radio frequencies, you have to have a license. So you've got to go to the FCC and you've got to get a license. I'm sure you've heard news coverage of, FCC doing spectrum auctions where they free up spectrum, take it from one vet person and then resell it to help fund the FCC for like cell phones are one of the probably primary ones that you'll see, stories about them auctioning off spectrum. That's the thing. You're buying basically the license to use those chunks of spectrum. So obviously Wi-Fi is great. Not everybody has the money to go out and buy a chunk of spectrum to use for themselves. So over the years, the FCC has opened up chunks of the radio frequency spectrum here for anybody to be able to use without a license, provided they follow certain rules, which are normally, for the most part, enforced at the manufacturing level, like we talked about earlier, by setting the standards for the manufacturers. So in the early days, it was 900 megahertz. Then we jumped up to 2.4. Then we jumped to 5, and then just in the last couple of years, they opened up what we call the 6 gigahertz spectrum, which is the largest chunk of spectrum. So one of the things that's been happening is they open up more and more different radio frequencies that we can use. They've also been expanding how much of those chunks are available. You can see there the 900 megahertz window there was only 26 megahertz in size, whereas the 6 gigahertz spectrum is 1200 megahertz that are available. So a huge difference in the available spectrum that's there in those newer opened up license-free spectrums that we all get to use. So one thing I want to talk about here just really quickly is the difference between dBm and milliwatts. They're both measuring the exact same thing. And what we find is in the early days, and still to this day for the most part, when you're looking at data sheets on business class products, you will see output power measured in dBm. So for dBm, you can convert that to milliwatt. And generally is basically as the dBm, for every 3 the dBm goes up, the milliwatt output power doubles. So that's why consumer equipment prefers to use milliwatts, because it's a lot more exciting to say, hey, we're offering 200 milliwatts and our competitors are only 100 milliwatt, rather than saying, hey, we've got 23 dBm, our competitors are 20. When you measure in milliwatts, the differences look much bigger, and they technically are. Now, so why is it not everyone has converted to milliwatts? Well, it goes back on the business side of things. Oftentimes you're doing link calculations. Maybe you're using external antennas, you're doing an outdoor link, you're adding antennas, you're adding cabling. So you measure loss due to cables and connectors and gain due to things like antennas using dBi. So you can take your dBi, take your dBm coming out of your radio, add in the dBi from your antenna gains, subtract out connector losses and cable losses in dBi, and get your total output power really simply by just doing simple addition. In addition, when you're doing calculations to calculate range and link budgets and things like that, it's all based on dBm, the mathematical formulas. So for that reason, business stuff generally uses dBm for power measurement. Consumer stuff tends to use milliwatt. Just some terms here. Signal to noise ratio. This is probably the most important thing when it comes to Wi-Fi quality, or the quality of your Wi-Fi connection. And it's something most people, at least that I've talked to, have no knowledge of or don't pay much attention to. So signal to noise ratio is basically the signal, what's being transmitted from your access point or from your client, versus RF noise, other sources of RF interference, whether they be neighboring Wi-Fi devices, other wireless devices, or just sources of RF interference coming off equipment. So that's your signal to noise ratio. How strong is that signal compared to the noise? And basically, the better your signal to noise ratio, the more reliable your Wi-Fi connection is and the faster speeds you can achieve. So as an analogy to try to explain that, think about going in an empty conference room or meeting room, you and a friend sitting across from each other, talking to each other. You've got a high signal to noise ratio. You can hear each other fine because the room's quiet because it's just you two in there. Take those two people, transport them to a nightclub on a Saturday night, and now you've got a horrible signal to noise ratio. They're still talking at the same level, but they have a hard time hearing each other because of the music and the sound of other people talking, glasses clinking, things like that. So that's the same thing that happens in the RF space. And then just another common term here is attenuation. It's just the term that you'll see used to describe basically how quickly or how much a radio signal degrades as it passes through substances such as air. So for instance, a signal will go much further in open air than it would if it's trying to penetrate concrete. So basically, the denser the material the signal has to go through, the more quickly that signal will attenuate and drop off and become unusable. And it's also something to take into account if you're doing outdoor stuff, because during some parts of the year, you may have relatively low humidity. Other times of the year, you may have lots of humidity. Certain times of the year, you may have trees with no leaves. Other times of the year, you'll have trees covered in snow or trees covered in leaves. So what happens is you'll do an outdoor deployment, everything will work great. And then a storm front will come through, humidity will jump up, and suddenly your links aren't being able to send data at the speed that they need to because the signal is now being attenuated due to the extra moisture in the air or other changes in the environment. Next up here is path loss. So if you actually want to calculate how far your Wi-Fi signal can go, this is the formula up here that you're going to use. Good luck. So we just have here also a list of just, some common things out there and how much attenuation you could expect to see. So for instance here, a window, just a standard glass window, can give you up to 3 dB of loss. And now if you remember what we talked about before with dB, every 3 dB doubles the signal strength, or in this case, every 3 dB loss would give you basically half the output power as measured in milliwatts. But it's not that simple as just being a direct relationship, with the signal strength. Again, this is the formula here to actually calculate it. So you can see a 3 dB loss here on your signal will give you effectively 70% effective range compared to not having that loss. Tinted windows, so they've got a glass coating on there. Those will double or more your loss going through that window. If you're in a home sending the signal through screens on the window, that will also severely impact the signal going through it. And then just as general, as things get more and more dense, the more loss you can expect to see. So Wi-Fi range. So the Wi-Fi range you're going to get is basically a combination of everything we've talked about. The signal strength coming out, the signal to noise ratio, where you're trying to listen to that signal, environmental issues with attenuation, the frequency being used, etc. But the thing people tend to overlook also is that Wi-Fi is two-way communication. Goes back to that analogy we were talking about before. You've got two people in a meeting room talking to each other, sitting across from each other in a quiet room. They can hear each other just fine. Now imagine one of those people has laryngitis. They can't speak as loud. So before, when they were both talking normally, maybe one could stand on one side of the room, one could stand on the other side of the room. They would hear each other just fine and be able to hold a conversation. But one of them now has laryngitis. They cannot raise their voice. And now they can't maintain that communication unless one of them gets closer to the other so they're both in range of each other. That's the same thing with Wi-Fi. What we often see out there is access points are 500 milliwatt, 1 watt, sometimes even more. But the client device that needs to talk to that access point is only got 25 milliwatts of power coming out of it. A lot of your little portable tablets and phones and things like that don't have a lot of Wi-Fi power. So because of that, your Wi-Fi range isn't dictated by your access point or your router. It's usually dictated by the client device and the ability for that client device to be able to get its signal back to the access point. And this causes one of those common problems we run into out in the real world, which is your Wi-Fi sucks, but you look at your phone, you can't get eBay to load up. You don't know why. Your phone shows you've got a signal. It's got a decent signal. It's not a great signal, but maybe it shows 2 bars or 3 bars, depending on which vendor's chip it or which vendor's phone you're using and how they interpret that signal strength. So I've got good signal. Why is it not working? And the answer for that is because your phone or your tablet or whatever is telling you how strong the signal is that it is hearing from your access point. It doesn't know how well the access point is able to hear the client device. So the client device says, yeah, I can hear that access point just fine. He's nice and loud. But the access point isn't able to hear your client device, and that's causing some of those issues. So another thing here I want to talk about a little bit when it comes to RF behavior is how radio waves work, right? We call them radio waves. And the interesting thing with this, and this is probably why we call them waves, is because they behave just like water waves as well, or very similar to how water waves work. You have a pond, you throw a rock in the pond, where it hits the water, that's where your transmitter is, whether it's a client or an access point, and you can watch those waves sort of radiate out in a circular pattern. And you will see if there's like a wall or other obstructions in the water, you can see the waves bounce off of those solid objects. You can see waves wrap around certain obstructions. Now, water waves can't penetrate a solid object like radio waves can. A little bit of a different there, but you see that same thing. So you end up in situations where that radio signal takes multiple different paths. Um, that take different amounts of speed. So you may end up here sending out one nice signal, and then over here at your client device, you may hear that signal coming from reflected off of this device, reflected off of this wall here, another signal coming through here a little bit quicker because it's got a shorter distance going through that solid wall. Although it's attenuated the strength, it's getting there first, etc. So you see some weird stuff. So that causes a lot of those problems you run into out in the real world, especially when you're dealing with metal in the environment, causing reflections and things like that, which can cause weird issues. And they're hard to diagnose and troubleshoot because you can't see what's actually going on with those radio waves and how they're bouncing around. Next here, I'm going to talk about how Wi-Fi devices transmit. So one of the things that's key here when it comes to Wi-Fi, ignoring MU-MIMO, ignoring the relatively recent advancement of MU-MIMO, one of the things that you run into is radio devices have to take turns broadcasting. You can't have multiple devices broadcasting at the same time using the same frequency. When you do that, you get interference. If you're old like me and remember analog walkie-talkies, you would run into that situation where you and one of your friends would both try to talk at the same time, and your other friend would just hear a horrible amount of noise. Or maybe you've been driving out in the countryside late at night and you get two radio stations that aren't normally close to each other, but are using the same frequency or neighboring frequencies, and they start to overlap with each other and you get weird sounds coming through. That's the same sort of thing that happens with the data that you're trying to send with Wi-Fi if multiple devices are trying to broadcast at the same time. So up until Wi-Fi 6, this is how it determined whether or not you could broadcast any data. You had a very simple little algorithm here, a flow, where basically, hey, I've got some data I want to send. So I will stop and listen to see, is anybody else broadcasting right now? If somebody is broadcasting, I'll wait a random amount of time and repeat the process until no one else is broadcasting, and then I'll broadcast my stuff. So when you're talking low speed, low intensity data back in 1997, this made a lot of sense, right? Why would you spend time and CPU power trying to coordinate whose turn it is to broadcast when this is going to be perfectly fine? Obviously not seeing a future where people are streaming audio and video and transferring gigantic amounts of files. So the problems you run into here is you can very easily run into a situation where multiple devices need to broadcast at the same time. Because there's no coordination, they may both decide to broadcast at the same time. They both listen at the same time and verify no one else is broadcasting. And then they'll decide at the same time to start broadcasting, interfering with each other, basically causing those packets to be dropped and need to be sent again. The other problem we run into, which is related to that, is the hidden node problem, where you've got two client devices that are in range of, say, an access point, but they are not within range of each other. So it's not possible for this laptop, in this case, to be able to hear that this laptop is broadcasting. So you run into these situations where they will both broadcast at the same time because they can't hear each other and they think the other one is not broadcasting, but your access point hears them both, and then again, packets get dropped because it just hears a bunch of noise. So that's the hidden node problem. Now, with Wi-Fi 6 and going forward, they have added technologies to help solve some of this issue, but you're still going to run into this until all of your client devices are using Wi-Fi 6 or better. And even then, the improvements only work in certain situations just to maintain backwards compatibility. Another thing I want to talk about here is data rate versus throughput. If you want to have some fun, pull up any Wi-Fi device on Amazon and start reading the reviews, and you will see lots and lots of complaints about this right here, data rate versus throughput. Now, There's different definitions for these terms, and those definitions do overlap. So this is the way I am using them to help try to explain this. So the data rate is the rate that if you pull up your Wi-Fi statistics, that's the connection rate that it's showing between, your laptop and the access point. Now that data rate, sometimes also called a physical rate or a link rate, that includes both the data you're trying to send. So if you're watching something from Netflix, the data that Netflix is trying to send you so you can watch the video, but it also includes all of the overhead that goes into Wi-Fi to make Wi-Fi work and seem to work nice and smooth. Throughput is what people measure with their speed test. So that's only measuring the data that you want to send. It downloads a file off of their server, tells you how long basically it takes, and then calculates the speed based on that, and then it reverses the process, uploads a file to the server that's a certain size. It knows how big the size is, and it's able to calculate, based on how long it took to send, what your speeds are. So it's only measuring the data that's being sent between your computer and the speed test server and vice versa. It isn't measuring the extra stuff that makes Wi-Fi work. Now, the reason why we have this discrepancy, at least in my opinion, is just because back in the days of early networking, when you were using Ethernet or you were using coax cables, there was very little overhead. So basically, the difference between the data that you're sending and the total data that's going out over that connection was almost the same, just off by a few percentage points. Where with Wi-Fi, there's a ton of overhead, right? Because you're broadcasting in this open, unlicensed space where you have to share with all these other sources of RF interference that you're fighting for. It's an analog environment, packets get dropped, things get done. So because of that, you have somewhere in the neighborhood of 40 to 60% overhead on top of the data you're trying to send that's being also sent between your device and the access point to make it work. So because of that, you will often see, hey, this product advertises itself as an N300. And I know I'm dating myself there, but when I tested it, I was only able to get, 150 megabits throughput. They're lying to me about the speed. And it's not we're lying, it's just networking equipment forever has always used the data rate, not, this measured throughput. So that's why you see that discrepancy. And that doesn't take into account the fact, distance from their access point, signal to noise ratio, whether their client device is actually even capable of achieving the maximum speed from the router, et cetera. So how do I increase speed? Now, this is not a question for you as someone deploying things. This is me sort of explaining how, from a Wi-Fi standards perspective, how we get those faster speeds when we go from N to AC to AX, et cetera. So we've got three main ways that you will see over the years that are used to increase the overall speed that's marketed here for you. One of them is increasing the encoding. So 11N used 64-bit QAM, 11AC used 256-bit QAM, 11AX offered a 1024 QAM, and now Wi-Fi 7 is offering a 4096-bit QAM. So QAM is just how many bits are being used and crammed onto those radio waves. So as that goes up, the amount of data goes up. And just like with Wi-Fi power output, as the QAM increases, the actual data extra data that can be sent doesn't increase by as much as the QAM does. So for instance, the jump from 1024-bit QAM to 4096-bit QAM is only about a 20% actual performance increase, even though the QAM, quadrupled. The next thing is spatial streams, increasing the number of spatial streams that we can use. And the other one is increasing bandwidth. So, and I will explain spatial streams here in an upcoming slide. And then bandwidth, just, how much of that available RF spectrum are you using at a time? 11G used 20 megahertz channels. You could only broadcast on 20 megahertz at a time. With 11N, they added the optional ability to broadcast on 40 megahertz channels. So you've doubled the bandwidth and you've essentially doubled your data rate just by doubling your bandwidth there. And then 11AC wave 1 gave us 80 megahertz channels. AC wave 2 gave us 160 megahertz channels. So let's talk a little bit first about bandwidth. So we're going to go through those things we just talked about sort of in a reverse order here. So we'll start off by talking about 2.4 gigahertz, which is, probably what most of you first got started on. And to this day, if you're buying smart plugs and a lot of different little cheap Wi-Fi cameras, almost all of them are exclusively 2.4 and do not work on 5 gigahertz. So in North America here, um, we have approximately 60 megahertz of 2.4 spectrum available to us. Those over in Europe and some other places have a little bit more than that, but here in North America, we've got approximately 60 megahertz. And you might remember me saying that 11G used 20 megahertz channels. So what that tells us is we've got 3 channels that can be used before there's interference. You can have 3 different access points or routers or whatever using a 20 megahertz channel, and you won't have any interference. But as soon as you add a fourth, you will run into interference issues because now you're using a total of 80 megahertz in the space and there's only 60 available. So there's going to be overlap, there's going to be interference, performance is going to take a hit. Now with 11N, we bump that up to 40 megahertz channels on 2.4. But again, we've only got 60 megahertz available. So the problem we run into is now you can have one access point in the area and you're fine. As soon as you add a second one, you're going to start running into interference issues. So generally the way 40 megahertz channels work is these sit right here in the middle. And this has to do with the way the signal sort of bleeds over down here on the edges, so band edge issues. So generally you run into a situation where even if your neighbor's only using 20 megahertz channels, if you're using 40 megahertz channels, you will have interference. And that's why most products, at least the consumer products back in the day, would sort of automatically fall back to 20, even if you told them to use 40, unless you were in, the bottom of a concrete basement where there were no other Wi-Fi signals. And that's why there was a big push starting with 11N and really got started with 11AC to move to 5 gigahertz channels. So you can see here, if we're using 20 megahertz channels here in the US, we've got, I think it's 26 non-overlapping channels. So you've solved that interference issue, right? You've got so much bandwidth available to use that you don't have to worry about it because there's so much here that you're never going to step on each other's toes, at least at first. So before I get into that, I do want to highlight here, notice how in the middle, there's this big section here that's highlighted in sort of a peachy orangey color, depending on your monitor. These are called DFS channels. So what happened is the FCC used to make 5 gigahertz to operate here, you had to have a license. So the FCC at some point decided that they were going to open this up for non-licensed use. And of course, the people who were already using this with their license solution says, hey, wait a minute, you're going to have all these people interfering with us. So what happened is the FCC created something called DFS. I believe it stands for dynamic frequency selection. For those legacy users. So if you're going to be operating on these channels that are designated DFS, meaning that legacy users may have been using them in the past, before you can start broadcasting and using these channels, you have to listen and make sure that there are no legacy users nearby. And if at any point you do detect a legacy user, you have to stop broadcasting right away. And just because of the way RF is and the imprecise nature of things, I mean, there's no special, identifier on RF noise that says, hey, I'm a legacy user. You sort of kind of have to, they try to guess at it. So there are sources of RF interference that may look like a legacy user, but aren't a legacy user. And according to the DFS rules, you have to stop broadcasting when that happens. So if you're broadcasting on a DFS channel, you think you hear a legacy user, you have to disconnect everybody and then switch to a new channel. And if you switch to a new channel that is also a DFS channel, you can't start broadcasting right away. There's a certain period of time you have to wait and listen to verify that channel is not being used. Now, some higher end APs like our WAC 650S have a third radio that does nothing but monitor DFS channels. So you can instantly basically switch to the new channel without having that pause. But most access points don't have that, so there's always going to be a pause. So if you're using DFS channels, your users may get disconnected at times, and there may be a brief delay while the AP finds a new channel to use, verifies it's not in use, and enables it, and then your client devices find that new broadcast and connect to it. So for that reason, a lot of you out there don't want to use DFS channels. There's another reason a lot of you don't want to use DFS channels. A lot of consumer equipment doesn't support DFS. And the reason for this, at least last time I looked into it, it added about 6 months to the certification process to get DFS certified. So because of that, a lot of consumer equipment just skips getting that certified at all. Some of the higher end, more businessy type stuff will launch without DFS support and then add it via software, via firmware or software updates, depending on the type of device. But most end users never update anything, and so a lot of your end user companies out there just never bother adding an upgrade to enable DFS. Surprisingly, a lot of Apple products don't support all the DFS channels. That's a very common problem. So because of that, if you're in a network that people are bringing their own equipment to, you may not want to use DFS because some of your users will complain they can't get on the network because they don't support those DFS channels. And this is something that our tech support gets calls about all the time, even from some very experienced VARs out there who've been doing Wi-Fi for a while. We had a case recently where they were deploying an IP set-top box type thing, and they did not realize their IP set-top box did not support DFS. And it was in a very crowded condo situation or MXU situation. So it really put a monkey wrench in things because suddenly all these channels they thought they had access to, they can't use anymore. So they went from 26, 20 megahertz channels down to, 9 non-overlapping channels. So for that reason, a lot of you just basically assume that these DFS channels don't exist because of the problems that using them may cause for you down the road. Now, you might also remember the reason we got here and the reason we're talking about this is we're talking about the bandwidth used, the channel width. So you can see, one of the ways we get the faster speeds is we increase the channel width. So with 11N, we added 40 megahertz channels. So now, if you're not using DFS, instead of having 26 channels and then 9 channels, now you're down to just 4 non-overlapping channels, which is probably good, more than enough in most environments, except for maybe really crowded MXU stuff, to be able to deploy, right? You can have 4 APs within, RF line of sight of each other, and you won't have any issues until you get the 5th. And that's generally, gives you enough space to space things out. Plus, this is 5 gigahertz, so it's not good at penetrating walls. So, it's good. But again, we want faster speeds, dang it. So with 11 AC, we gave you 80 megahertz channels. So now you're down to just 2. You're in even worse shape than you were with 2.4 back in the day. At least then you had 3 non-overlapping channels. Now you're down to just 2 non-overlapping channels. And then with 11 AC Wave 2, we added 160 megahertz channels. So in order to use 160 megahertz channels, you have to use DFS. So a lot of you will never see the fastest speed that your access point or router can provide because you don't want to use 160 megahertz channels because your client devices don't support DFS channels and can't connect. But that's how you would get those fastest speeds, is using 160 megahertz channels. And then Wi-Fi 7 has added 320 megahertz channels. So, as we get those faster speeds, it becomes harder and harder to actually achieve those speeds in a real world environment where there are other devices and other access points around. Works great in a concrete bunker. So now the next thing we're going to talk about is spatial streams. So spatial streams, you might remember before I showed you that slide showing you how, radio waves can bounce off of things and take different paths and create sort of echoes. That's what we call multipath. The fact that you're getting the same signal comes out here and it radiates out, bounces off of things, and you end up getting those radio waves hitting the receiver and getting a sort of echo effect because something that travels direct line of sight covers less distance than something that's bouncing off of various objects in the environment, which are going to take longer because the distance that they travel is longer. So you get a sort of echo effect. That was what we called multipath, and it was something that was just the bane of our existence back in the BG days. Starting around 802.11, they started finding some solutions to that and started turning this actually into a benefit. So what used to be the bane of a Wi-Fi installer's life here turned into something good for us by allowing us to take advantage of these different paths. How it works exactly, I couldn't tell you. It's way above my pay grade, but just in general, you use multiple antennas, you send different data on each antenna, and you take advantage of the fact that the antennas are offset from each other. And because of that, the signals will take slightly different paths with slightly different timing. So you can broadcast two different data streams at the same time using the same channel and frequency, but different data on each antenna. And because of that spacing and because of some smart people stuff that I don't fully understand, you're able to then combine those together into one faster stream. So for each antenna you have, in theory, you've got a different spatial stream you can support. So the first time we encountered this was probably back in 802.11n with N300. So the maximum speed you can send data with 802.11 is 11n is 150 megabits per second. But of course, we have N300 products, N450 products, so which are providing 300 megabit data rates or 450 megabit data rates. And they're doing that by using these spatial streams, taking advantage of the slight different paths, different data will, or different signals will send based on the antenna it gets broadcast out of, and are able to put different data on there. So one antenna is sending 150 megabit stream. A second antenna on a 2x2 system, a two spatial stream system, is sending a different 150 megabits per second data stream. And then your client device receives both of them and combines them together so it appears as one 300 megabit data rate. In the case of 450, you would have three antennas sending three different data rates or data streams at the same time to combine together for 450. So that started hitting the market with 802.11n. With 802.11 AC, we started getting what we call MU-MIMO, multi-user MIMO. So MIMO is multiple in, multiple out. That's what we were using before on this previous slide is MIMO. Now we've got multi-user MIMO. So we're doing the same thing. We're sending two different data streams here on one data stream per radio. But instead of being combined together by one client device as one 300 megabit stream, you can take advantage of the environmental effects here to send 150 megabit data stream to one user and a different 150 megabit data stream to a different user. So that way you could in theory have, one AP simultaneously sending data to two different client devices instead of having to take turns like you normally do. Now with Wi-Fi 6, they added an enhancement to multi-user MIMO that allows multiple client devices to send data back simultaneously to the access point. So basically the same thing here, just in the opposite direction. Which leads us here to talking about spatial streams. So you will always find spatial streams denoted on business class products on the data sheets. In fact, oftentimes if you're looking at the data sheet and you're looking to find out the speed of the access point, you will not oftentimes see, AC 1800. You will just see 11 AC 3x3. So from a technical perspective, they're just assuming what the max data rate is that 11 AC can support per spatial stream and can do the math yourselves. And that also can take into effect, your client devices. Are you going to be using 160 megahertz channels? Or are you only going to be using 80 or 40? How many spatial streams does your client device support? So you can it's more helpful that way, I think, and that's why you see that way on data sheets. So what you will usually see on a access point or router data sheet is something like 2x2, 3x3, 4x4. The first number is how many spatial streams your device can transmit. The second number is how many spatial streams your device can listen to at the same time. So if you're looking at, say, most vendors' product, it's going to be 2x2, 3x3. If you're looking at Cisco equipment and our new Pro Series NWAs, you will see a number followed by a smaller number after a colon. So you will see, for instance, 4x4 colon 3. So you've got 4 antennas that can transmit, 4 antennas that can receive, but you can only actually use the number after the colon. So in this case, 4x4 colon 3 means you can only actually use 3 of those antennas at any one time, even though you've got 4 to choose from. And that works in both directions. It's just a little something there to help with RF noise. In theory, the AP or whatever can decide out of those 4 antennas, which 3 are going to provide me the best quality signal. It's more of a benefit on the receive side than on the transmit side. Now, if you're looking at client devices, though, the numbers won't match. You will very often see 2x3, 2x4. And so what happens is a lot of client devices, the assumption is they're going to be downloading a lot more data than they're going to be sending. So in order to cut back on cost, cut back on energy utilization, they can receive more data streams than they can transmit back. So they can download faster than they can send. So putting it all together here, you combine the number of spatial streams supported, the modulation type supported, and the type of modulation supported depends on the client device. It also depends on the signal to noise ratio. One of the first things your client device is going to do if it doesn't feel that this signal to noise ratio is good enough is it's going to drop the QAM. So to get that maximum quad modulation, you have to generally have a really good signal to noise ratio. And then what ratio or what bandwidth are you using for your channels? And that's how you end up finding out what the maximum speed is you will see. So for instance, here when dealing with 11 AC wave 2, if you have an access point that's 2x2, you will see a max speed claim of 1750 for the 5 gigahertz radio. So that's assuming maximum modulation type, maximum channel width. But again, most of you probably aren't going to use 160 megahertz channels. You're probably only going to use an 80 megahertz channel. So now that drops our max data rate down to less than 900 megabits per second. And then you may not get 256 QAM, you may have poor signal to noise ratio. So you'll drop to 64 QAM, and now the maximum data rate you can achieve is 650. Next up, we're going to be talking about one of the questions we get most often. How many clients can I get on your access point? So what I'm going to tell you is it has nothing to do with your access point or router. It has nothing to do with that number that's on the data sheet. It doesn't matter if that data sheet says 256 users, 512 users, 1,024 users. None of that matters. What matters is airtime. And you're going to run out of airtime long before you get to that maximum number of users, unless all your users are just associated with the AP and never transmitting data. In the real world environment, you're going to hit the maximum number of users long before you get anywhere near the number that's on your data sheet. So we'll give you sort of an example here as to how that works. So in this situation here, we're going to be watching a video stream. We've got a bunch of users. They want to watch a video stream here for you. And this video stream is encoded at 3 megabits per second. So in order to watch the stream, every user has to get 3 megabits per second available to them. And in this situation, the only thing we're changing here, we're not changing signal to noise ratio, we're not changing bandwidth available, we're not changing any of that. The only thing we're changing in this example is the spatial stream. So if our client devices support 3 spatial streams, we can get 34 laptops on that access point watching that 3 megabit stream. If we change the client device to a client device that only supports 2 spatial streams, now we can only fit 21 users on that same access point. Nothing's changed on the access point, but the airtime utilization, how efficiently we can use that airtime utilization goes down because we're only able to use 2 of those available 3 spatial streams. And then if we switch to something that's only got a single spatial stream support, now we can only have 10 users watching that same 3 megabit per second video on that same access point. So that's just taking a look at your spatial streams. Obviously, out in the real world, this gets a lot more complicated. You've got different types of client devices with different types of spatial streams each. You've got different types of traffic that need to be supported. You've got different signal strengths and different signal to noise ratios based on where those users are in relation to your access point, et cetera. But the main takeaway here is just to show you how much difference just one of those factors applies in there. And in all of these cases, you're bumping up on the user limit based on what they're doing, not based on any limitation on that access point. So I want to talk a little bit about our smart antennas, and I'm going to go through this pretty quick. Basically, what is co-channel interference? Co-channel interference is basically anytime you've got something else using that same channel that you're trying to send data on, and it causes interference, right? We spent all day talking about the interference issues when you have different devices using the same channel. That is called co-channel interference. And generally in a network deployment where you control all the access points in the environment, the traditional way of dealing with this is you turn down the power on your access points so the signal doesn't go as far. So the signal strength from those access points more closely matches what your clients have. So that way APs are not interfering with other APs. Now, the downside of doing it this way is it also tends to lower your signal to noise ratio, which lowers your QAM. So the overall data speeds that a client device can see, especially as they get further away from the access point, is going to decline, but it's a manageable decline, and it's one that, still maintains a high quality connection. Where with interference issues, you never know when those interference issues are going to start causing problems for you. So that's how you would traditionally handle it. So we have a technology in some of our access points, and to know if our access point has a smart antenna, you just look for the letter S at the end of the model name. So WAX650S, smart antenna. WAC5302D-S, smart antenna. Is we have this smart antenna technology. If you've worked with Ruckus in the past, you're familiar with their BeamFlex Plus technology. It's basically our version of that. And what it does is instead of having a single fixed antenna pattern, which is what most access points have, we have an array antenna in there that can go through hundreds of different antenna patterns and choose the antenna pattern that focuses the beam to where the client device currently is. And on our algorithm that we use, it can also look at other sources of RF interference and choose an antenna pattern that helps ignore that interference at the AP level. So because of that, you can cram a bunch of APs in the same area, and you can actually achieve greater than 100% airtime utilization, because the smart antenna basically allows two different smart antenna APs to operate at the same time without interfering with each other or minimizing the interference. And smart antenna works with mobile client devices. It works with any client device, so it doesn't require any special technology on the client, and it operates and updates the antenna pattern as the client devices move around, something that isn't really supported with like beam forming. So next up here, I've got a little test situation. This is an actual real world scenario. This is I believe it was a hotel, and the hotel is doing 1 AP per room. These are the little lower powered wall plate APs. So we decided to use this for our test. As you can see, there's two different floors, and we're going to be using APs broadcasting on channel 100, 5 gigahertz. And none of them are directly next to each other. There's some spacing between them, but they do still cause interference. The signal goes a lot farther than you realize sometimes. So in this test, we took our product, a NWA 1302 AC and a Ubiquiti UAP AC IW. Both have almost identical specs, with the primary difference being the smart antenna. We have one, Ubiquiti does not offer our type of smart antenna. So with just one AP turned on, they beat us by just a little teeny tiny bit. They were able to achieve an aggregated throughput of all clients of 406 megabits per second. We had an aggregated throughput of 404 megabits per second. Both were roughly 67% airtime efficiency. Turn on a second access point, and you will notice the aggregated throughput on Ubiquiti is now 555 megabits per second. With us, we were able to achieve 785 megabits per second aggregated throughput between all users on both access points. And that's where the smart antenna is kicking in and helping eliminate some of that interference you would normally run into. And you also hear, if you look at channel efficiency, basically 95% airtime utilization with Ubiquiti. But because of our smart antenna, we were able to achieve 131% airtime utilization. And as we turn on 3 APs now, we continue to see the same thing. We've now got over 900 megabits aggregated throughput, where Ubiquiti is basically capped out at 544 megabits throughput. Airtime utilization on the Ubiquiti actually went down to 91% efficiency, just because there's a lot more rebroadcast. And again, like I said before, when people are choosing when it's time to broadcast it, there's a lot of little problems there. In the case of our AP, APs, we've now achieved 155% airtime utilization. So airtime utilization actually went up even more as we added that third AP because of that smart antenna. The other thing I wanted to draw your attention to here is you will notice the available bandwidth, aggregated bandwidth per AP is roughly the same between all 3 APs. So with the smart antenna, you're able to basically more efficiently share that limited airtime that's available. Whereas on Ubiquiti, some very big differences and inconsistencies between the APs as they sort of fought with each other for that limited bandwidth that was available. So that's smart antenna. Another technology we have is called dual optimized antennas. If you're looking for something that's can't afford smart antenna, this might be something to look for. So with this, generally the last letters on the model name are going to be D or D-I or dual optimized. So basically your standard access point, including most Zyxel access points, just have a fixed antenna pattern. There's one set of antennas there. They're optimized with the idea that you're mounting your AP on a ceiling above the area to be covered, and then it radiates the signal out and downwards below it. Unfortunately, in the real world, you often end up having to mount your access point on a wall. So it's not optimized for that wall deployment. A lot of your signal goes up into the ceiling, down into the floor, may cause interference on multi-floor buildings. It's just not ideal. So our dual optimized antenna APs have 2 sets of antennas. So they can use a traditional ceiling mount antenna pattern or an antenna pattern that's optimized for wall. So this allows you to choose on a per AP basis which antennas to use based on where you've deployed that particular access point. So now just some general rules of thumb when it comes to mounting APs. Again, most APs are optimized to be mounted directly above the area to be covered. So that's what you want to do. You want to mount them above the area to be covered, and within reason, you want to mount them as high as possible. And the reason for that is you're trying to, the signal goes better through open air than it does when it's having to go through people or cubicles or whatever. So because of that, you mount it high enough that the signal can go from wherever the client device is directly to the AP without having to transmit through physical objects. As you lower the access point down, it's more likely that the signal is going to have to go through people or cubicles or whatever to reach your access point. So as high as possible within reason. As you're mounting it up there, you do want to take into account the fact that if you're mounting it really high, above a drop ceiling, for instance, you may have metal ductwork up there. You may have conduit, things like that. So metal and Wi-Fi signals don't get along because metal is very dense and it's reflective. So for those type of situations, you may need to actually drop the access point down a bit to make sure it's not trying to send signal through metal. It's very common for people to mount these access points on the drop ceiling itself. However, we often run across end users who are like, no, I don't want you poking holes in my drop ceiling to run Ethernet through them. So provided your local building code allows it, you can often just rest the access point on top of that drop ceiling. The drop ceiling itself is usually a very light material. It's not very dense. And because of that, the RF signal is able to penetrate it pretty easily. So again, provided your local building code allows you to do this, set the access point on top of a drop ceiling, not going to have much difference as far as performance goes than if you had mounted it underneath the drop ceiling traditionally. And that way you've got a happy end user because you haven't poked any holes in his ceiling. So when it comes to hotels, the traditional way of doing hotels is what we call umbrella coverage. You would usually put the access points out in the hallway, and one access point would cover anywhere from 4 to 16 rooms. We find that for the most part, this has gone away. A lot of your cheaper budget hotels are still trying to do internet this way. Although for most of your mid-tier and higher hotels, and most of your new builds, they're going for in one AP per room or one AP per every other room. Us and just about every other vendor out there makes lower powered wall plate APs specifically for this application. These APs usually have Ethernet and PoE pass-through ports, so you can run one CAT cable into the room to your AP and then run CAT out to it to your IP set-top box, to an IP phone, etc. in the room, so you're not running as much cable to those rooms. And the reason for the switch, other than just the convenience of just doing one Cat 5e or Cat 6 cable to the room for everything, is also has to do with how Wi-Fi is being used. In the old days when I first got started 20 years ago, you know, most people didn't have Wi-Fi. Only the business guy was getting on there with his work laptop to send a few emails or whatever it happened to be. And now everybody wants to get on internet. Everybody wants to stream video. So you've got more users than ever per room. Those users are using more and more bandwidth, and umbrella coverage just doesn't work in those environments. Another very common problem you run into with this umbrella coverage is it's very normal for the bathrooms and the plumbing to be along the wall that borders the hallway where you're mounting your AP. And again, Wi-Fi doesn't like metal. So what happens is, the user's trying to use their cheap $39 Walmart tablet sitting on their bed. It's got to get that through the bathroom wall, through the bathroom, through the shower tub installation in the dense tile, through the plumbing that's in the wall, out into the hallway. And the signal just can't make it that far. And then you throw in overcrowding of those APs, and it just makes it that much worse. If you can, be sure that you're mounting these APs where users can't see them. Users in hotels will steal anything that's not locked down. And then if you've got LEDs on there, turn off all the LEDs you can. A lot of people are paranoid. They see those lights flashing. They think someone's spying on them somehow. Or they just don't like the lights. It interferes with their sleeping patterns because they've got something blinking at the peripheral of their vision. So turn off the LEDs if the AP allows it, or mount it someplace where they can't be seen. I used to travel a lot for business, and I can't tell you how many times I've gone into a hotel room and found an access point in the room or a smoke detector or something like that, and people have wrapped paper around it or towels around it, either paranoid that there's a camera hidden in there or just don't like the lights. And then just when it comes to planning, plan each area separately. So again, rooms, you would generally do one AP per room or per every other room. But then the other public areas, plan them individually. Meeting rooms, take them one by one. Expo centers, plan them individually. Plan your lobby separate from your hotel, restaurant, etc. And when you're setting those up for doing things like load balancing or client steering, you want to set those up in groups based on the physical location. We've had partners go in there, set up load balancing, and they just turn it on. They don't set up groups. So you've got your access points trying to force users in the lobby to connect to someone on the fifth floor because that AP isn't being used. So you create groups in your configuration when it comes to load balancing and stuff like that to make sure that they're load balancing in the physical area. Anywhere you've got a lot of users, you want to use smart antenna. For schools, it depends what type of classroom it is and what they're doing in that classroom. In general, a standard classroom, you would just put one access point in there. But it really comes down to what those users are doing. Is this a smart classroom? Do each student, are they expected to be online the entire time they're in class? Or are they only getting online at the end of class during free study sessions? Is this a smart classroom where instead of projecting, videos or PowerPoints onto a wall, they are streaming that directly to each individual client device? We have run into that where you've got 35 students in a room, and when the teacher wants to play an educational video, it streams that to all 35 users on their own Chromebook that they have. So obviously, if you're doing something like that where you're utilizing the Wi-Fi more, you may want to have multiple APs in that room. If it's a room where you don't have a lot of that, just used for browsing the web, not for streaming video. You can get by with less APs. Our Nebula and our local controllers both have a special load balancing mode specifically for smart classrooms, with the understanding that, every 45 minutes, 20 to 40 people are walking in, connecting to that Wi-Fi all within a few seconds of each other. So generally, what I would say, if it's a smart classroom and you've got more than 20 students, try to do 2 APs. And for any classroom with 30 or more students, smart antenna is the better way to go. Obviously we've seen people get by with less than this. It just depends on how that internet network is being used in that classroom. So let's talk a little bit about Wi-Fi 6, aka 802.11ax, and Wi-Fi 7. We'll start by talking about Wi-Fi 6. So Wi-Fi 6 is designed to work on all RF frequencies. A lot of people don't realize that there are 802.11ac, or now Wi-Fi 5 products. Wi-Fi 5 or 11ac is only on the 5 gigahertz radio. Your 2.4 radio on those products is still 802.11n. So with Wi-Fi 6, you can upgrade both your 2.4 radio, basically 2 generations, and your 5 gigahertz radio, 1 generation, to Wi-Fi 6. Wi-Fi 6 was designed specifically to counter a lot of these issues that we run into, due to legacy, the legacy 802.11 standard, and is specifically designed to help deal with modern deployments where you've either got a lot of users on one AP, or you've got a lot of APs and a lot of users in the same area. So a number of technologies here to make it operate a little bit faster. Final approval of Wi-Fi 6 wasn't until Q1 2021. Even though there were Wi-Fi 6 products behind that, a lot of those first-gen products are missing some of the Wi-Fi 6 features because they were based on an earlier draft where things had not been fully hammered out. So the hardware itself doesn't support all of the Wi-Fi 6 features, but you will still see those products marketed as Wi-Fi 6. Something like UL MIMO, which is basically the ability for multiple clients to send data back to the same AP at the same time without interfering with each other. That was only added to the Wi-Fi Alliance certification process in January 2022. So just some things to keep in mind. Some product that's using cheaper Wi-Fi 6 chipsets, or that is using older Wi-Fi 6 chipsets because they're cheap, is missing some of those Wi-Fi 6 features. So when it comes to Zyxel, all of our small business products, so anything that's NWA and 3 digits in the model name, or anything W starts with W, those all have full Wi-Fi 6 feature support. But you will see a number of products out in the market that don't, and they won't draw your attention to that, including us. So like, for instance, our NWA 50 and 90, they don't support all of the Wi-Fi 6 features. I call that Wi-Fi 6 Lite. Unfortunately, I couldn't convince our competitors to do that too. They just call it Wi-Fi 6, so we kind of have to too. So that's something to keep in mind. In addition, some vendors, for instance, some of the lower end Ubiquiti Wi-Fi 6 APs, they only put the Wi-Fi 6 on the 5 gigahertz radio. That 2.4 radio is still 11N. So all of our APs that are Wi-Fi 6 are Wi-Fi 6 on both radios. So after Wi-Fi 6 came about, the FCC and some other regulating bodies around the world decided to open up a chunk of spectrum in 6 gigahertz. So this is where Wi-Fi 6E comes in. The E stands for extended, so it's extending Wi-Fi 6 into 6 gigahertz RF spectrum. So 6 gigahertz gives us 2.5 times more capacity than Wi-Fi 5. There are no legacy devices indoors. So you don't have to worry about getting interference from older devices that are on there, or being slowed down by older devices, having to force your AP into, interoperability mode. You've got 7 non-overlapping 160 megahertz channels. So just to sort of visualize that for you, 6 gigahertz has more bandwidth available in 6 gigahertz than 2.4 and 5 combined. It's a huge chunk of spectrum there for us to play with and be able to use these faster speeds without having to worry about interference. There are some concerns when it comes to Wi-Fi 6. So one of those were, just like with Wi-Fi 5, or excuse me, with 5 gigahertz, there were legacy users. There were already people using 6 gigahertz, particularly utility companies and news reporters to stream video back to a tower. Um, so we don't have quite the same problem that we had with DFS, but we do have something else here. So the good news is 6 gigahertz doesn't go as far, right? It's a higher frequency, it's got less range. So if you're using Wi-Fi 6 indoors, you don't have to worry about causing interference to these legacy users or the legacy users causing interference to you. Where we run into issues here is if you want to use 6 gigahertz outside. So the FCC has put in place a new method of dealing with these legacy users. Basically, if you want to use 6 gigahertz outside, you have to use a third-party solution and register with them and say, here's where I'm physically located. Here's the channels I'm using. Are there any legacy users nearby using that channel? Yes or no? If no, you can go ahead. If yes, they'll coordinate with you to tell you what channels you can use. So about a year ago, the solutions for that would allow you to do that got sort of a preliminary okay from the FCC, but the FCC has never, as far as I'm aware, finally certified any of those solutions. So if you're trying to do 6 gigahertz outdoors, you're kind of out of luck at the moment. While we wait for the FCC to fully ratify those, there are some solutions that use like these preliminary certifications to do outdoor 6 gigahertz, but for the most part, no, not right now. In addition, there's a bunch of lawsuits against the FCC from those legacy users as well, trying to stop Wi-Fi from outdoor utilization at all. Probably not going to succeed, but they're trying. Which leads us to Wi-Fi 7. I know, guys, it's been a long presentation. We're almost done. So here is Wi-Fi 7 is something relatively new for us. We just launched our first Wi-Fi 7 AP last month, and it is available for you to purchase through our distribution partners today. So Wi-Fi 7 more than doubles the speed of Wi-Fi 6E. So we've got a faster theoretical top speed. Part of the way they've done that is by increasing QAM. As I mentioned earlier, we went from 1024 to 4096 QAM. They've doubled the channel bandwidth again from 160 megahertz channels in Wi-Fi 6 now up to 320 megahertz channels. And they've added some new technologies here. MLO, multi-link operation. So historically, client devices only connect to one radio on your access point, regardless of how many radios your access point has. With Wi-Fi 7, it now becomes possible for client devices to connect to 2 or 3 radios on your AP, and they can use that either to increase capacity or to reduce latency and increase reliability by sending the data across those different radios simultaneously. And in the future here, Wi-Fi 7 will have multi-AP coordination. So that APs will be able to coordinate with other APs in the same vicinity to better able to allocate the available spectrum and share it between them. So here's your quick summary of all the different Wi-Fi technologies. Short version here is Wi-Fi 7 works on all radios, 2.4, 5, and 6, just like Wi-Fi 6E did. Bandwidth goes up from 160 megahertz to 320 megahertz, higher QAM. The number of spatial streams that can be supported goes up. Wi-Fi 6 supports 8 spatial streams. Wi-Fi 7 can support up to 16 spatial streams. So for Wi-Fi 6, the maximum theoretical data rate would be around 10 gigabits per second. With Wi-Fi 7, that jumps all the way up to 46 gigabits per second. Now, one thing you will notice here is the launch date for Wi-Fi 7 is 2024. And if you're scratching your head saying, Sean, I've seen Wi-Fi 7 products on sale all year long, I understand the confusion. And what happens with all of these products, just like with Wi-Fi 6 and Wi-Fi N and 11AC, is that people want to rush out and get product onto the market using the new technology. They do not wait for the final certification or ratification of the standard. So they all rush to market, including us, with products based on the current draft. And then when the final version comes out, Some of those features may be able to be supported with the firmware update, but some of those newer features will require new hardware. So you end up in a situation like Wi-Fi 6 where the early hardware doesn't support all of the Wi-Fi 6 features. You will see that with Wi-Fi 7 as well. And to make it even more confusing, Wi-Fi 7 is going to have two different stages. There's going to be a release 1 sometime next year and a release 2 sometime in 2025 probably. So for instance, that multi-AP coordination, I believe that's not going to see the light of day until release 2. So you're looking probably 2025, 2026 before you see any hardware that supports that. So 6 gigahertz, whether Wi-Fi 6E or Wi-Fi 7, is good for high density deployments. You've got a ton of bandwidth available for you, no legacy users. So it's great for those high density environments because you can cram a lot of users in there. It's good for those applications that need a lot of bandwidth. You will often see companies marketing the idea of streaming virtual reality because of these faster speeds, which is true. You don't have to, you reduce the latency a little bit because you don't have to encode the video and then or encrypt the video, or what am I saying? Compress the video and then decompress the video when you receive it. You can just send raw data. You've got fast enough speeds to support that. So those are what you're going to see. You're also going to see 6 gigahertz used today in a lot of applications for providing mesh using the 6 gigahertz radio for the backhaul, because as it exists today, there's very few client devices out there that support 6 gigahertz, and there's almost no devices that support Wi-Fi 7. Google Pixel 8 is out there now, supports it. Apple just got around to adding 6E support on the 15. So you're looking at least another year, if not longer, for Wi-Fi 7 support on your Apple devices. So you've got the 6 gigahertz radio. It's fast. It's got a ton of bandwidth, but no one's really using it today. So use it to do mesh networks, to spread out coverage in your environment without having to run Cat5 cable. Use 6 gigahertz for the backhaul, and then that way your 2.4 and 5 gigahertz users still connect on those radios, and you don't have to pause to retransmit the data. It will be retransmitted instantly over that 6 gigahertz radio without causing interference. So that is it for today's presentation. I know it is long. I have not seen any questions come in. If you did have a question, send it in now using the question and answer part of the Zoom interface. Most of our webinars are recorded, and we do upload those to our YouTube channel. There's lots of Zyxel YouTube channels. So for here in North America, Zyxel America channel is where you want to go to find any of those presentations you've missed or you had to duck out on. You will also find video case studies, some best practices videos, and other things like that on our channel. And you can always connect to us at Zyxel US channel. I am not seeing any questions coming in. I'll stick around for just another second. Do check out our user forums, forum.zyxel.com. It's where you can get in touch with your fellow Zyxel users. It is monitored by our R&D and product management teams. Sometimes they will actually respond to things there. It's also usually one of the first places where security bulletins, release notes, etc., are published. Okay, I have no questions, so I'm going to go ahead and end today's webinar. Thank you for joining today.